In this video, this is going to be our first Vsepr video. So before you continue watching this video, you should have in front of you printed out those Vsepr tables from the PowerPoint presentation, because we're going to be going through examples from that, actually using this modeling software, so you have an idea of how this looks in 3 dimensions. So if you don't have that out in front of you, you want to pause this video, go get those Vsepr tables from the PowerPoint, print them out so you're able to look at those at the same time you're watching some of these molecular modeling simulations. So the very first molecule we're going to do is BeH2. And if you're looking at your Vsepr table right now, you have the Lewis structure for that. Now, everything in Vsepr is based upon what's happening with that central atom. So when you're looking at that central column on that table that has a Lewis structure in it, we're looking at that central atom. And everything to the left of that table, the number of the electron groups, the bonding groups, and the lone pairs, all refer to what's going on in that central atom. So when you're looking at BeH2, what you're seeing is, if you're looking at the beryllium, number of electron groups around that central atom, well, there's 2. Of those 2 groups, the next 2 columns ask how many are bonding groups versus how many lone pairs. You see, of those 2 total electron groups, 2 of those are bonding groups, no lone pairs. So I'm going to go ahead and build this molecule right now in the software. So I'm going to make the exact same molecule that you have on your paper. So when we're looking at this molecule, the purple ball would be the beryllium, the hydrogens would be the white balls on the outside. So for all these models that we're dealing with, the sticks coming out of the central atom are going to represent the electron groups coming off of that central atom that are involved in bonding. Later, we'll kind of show you what lone pairs look like. So now we're ready to actually see what this molecule looks like in 3 dimensions. We can rotate this molecule around in any direction that we deem fit to try to get an idea of how this looks when we're looking at this in 3 dimensions. So we usually try to describe the shapes and the geometries that we're seeing in these different shapes. So the column just to the right of the Lewis structure column asks for the electron pair geometry. So what that's referring to is how are these 2 sticks, how are the electron groups coming off of the beryllium related to each other? And you can kind of see that they're opposite each other. So that opposite relationship we call a linear relationship. If I go down here and click on the electron geometry, you see it's going to come up as linear. Now the molecular geometry, that refers to how are all of the atoms situated with respect to each other. And you can see, because each electron group deals with a bond to another atom, that not only are the electron groups appearing in a linear geometry, but the overall molecular shape of this geometry is also linear. So you can see that linear geometry. Now right away, even without the bond measurement, you can kind of see that anything that's linear, you should be thinking about this being in a straight line. So if I show the bond angles here, bond angle refers to what's happening between outer, central, and outer. What is that bond angle? And even if I move the molecule, it's always going to come back to that 180-degree angle for that linear orientation. The next column, the hybridization, we're going to leave alone for right now. We will come back to deal with hybridization for all these molecules in a later video. But we do want to look at this polar or non-polar. Now this refers to the entire molecule. We already talked a little bit about polar and non-polar individual bonds when we talked about electronegativity. But this is looking at what is happening with that entire molecule. So to do this, you do look at the individual bonds. And what's easiest to do is, whether it's true or not doesn't matter, always imagine the outer atoms as more electronegative than the central atom. And the reason being is that gets you at that idea of a pole. What's going on with the pole for the electrons? And that's going to help with some non-chemical analogies that we're using. So if I imagine the outer electrons are more, or sorry, the outer atoms are more electronegative than the central atom, this outer atom on the left is pulling on the electrons from the central atom. So I got a pull going to the left. I'm also going to have a pull from the right outer atom pulling on the electrons that are being shared with that central atom. I have two equal strength poles because these are the same outer atoms, and they're situated 180 degrees apart. So being they're situated 180 degrees apart and they're pulling with equal strengths, those poles would cancel out. So being those individual poles cancel out, this would be a non-polar molecule. Everything cancels out. One way of thinking about this, the non-chemistry analogy I want to use with you for this is imagine a game of tug of war. The outer atoms are competing against each other. The central atom is kind of that middle part of the rope. If you have a game of tug of war where each team has exactly equal strength and they're situated directly opposite each other and they start pulling, no one will ever win that game of tug of war. And as a result of that, all the individual poles are going to cancel out. This is going to be non-polar. Now, for that last column, this last column of polar or non-polar refers to the specific molecule we have listed. If we were to change one of these atoms, if I were to change this hydrogen to a fluorine, well, now fluorine is very, very electronegative, more so than the hydrogen. So even though the poles would be in the opposite direction, fluorine's pole would be much stronger than hydrogen's pole. As a result, there would be a net pole in this. Someone would win the game of tug of war if we kind of use that non-chemical analogy. And instead of being non-polar, this would be polar. But in this specific example, being these are the exact same outer atoms and they're situated equal and opposite apart from each other, this is going to end up in a non-polar molecule. No one's going to win this game of tug of war. So this is this first molecule we're seeing. And what you're going to see is anytime you have, looking at your Vsepr sheet, anytime you have two electron groups, that electron pair geometry is always going to be linear because that's the farthest apart you can space two electron groups is 180 degrees apart from each other. I'm going to go ahead and deselect everything so we can show our next molecule. So now looking at the Vsepr sheet, the next molecule is BF3. The Lewis structure is already drawn out for you. So when you look at that Lewis structure, you're looking again at that central atom, that boron. You're going to see 3 total electron groups. And of those 3 electron groups, 3 of those are bonding groups, no lone pairs in there. So if I kind of draw this molecule using this modeling software now, this is what the molecule will look like in 3 dimensions. Now right away, you're going to notice something. It doesn't quite look like how I drew it in the flat Lewis structure. Lewis structures in and amongst themselves do not try to convey any 3-dimensionality to it. The information contained in the Lewis structure, however, is able to contain this information. And that's what these Vsepr tables are all about, is extracting that information that's contained in the Lewis structure in order to really see what's going on in 3 dimensions for that molecule. So I kind of drew this molecule, and we can kind of spin it around, and you can look at it, you can rotate it in any different way you want, but we want to try to describe the orientation, the geometry of these 3 electron groups. So they're kind of arranged in a triangle, and you've already seen that they're all in the exact same plane. So the term we use for this, no surprise, is going to be trigonal planar. Anytime you have 3 electron groups, that electron pair geometry is going to end up being trigonal planar. Next, we want to look at what's the molecular geometry. So how are the atoms situated with respect to each other? And the atoms are situated with respect to each other also in the exact same orientation that the electron groups were situated with respect to each other, because every electron group on that central atom is involved in a bond. So what that means is that the molecular geometry is going to match that electron pair geometry, and you're going to get a trigonal planar arrangement again. We kind of look at the bond angles here, and this is where you can't get stuck thinking and looking at a two-dimensional Lewis structure. You have to use that Lewis structure to go on and to deal with something in 3 dimensions. So when I throw the bond angles up here, you're going to see that these outer atoms are equally spaced apart, and they're all 120 degrees separated. Not at all how I chose to draw the two-dimensional Lewis structure. If you go back and look at the Lewis structure that I drew, it doesn't look like they're 120 degrees apart. Instead, they're 90 and 180 based upon how I drew it. But how you draw the angles in the two-dimensional Lewis structure doesn't mean anything. It's how will that molecule really look in 3 dimensions. And in 3 dimensions, it's going to be 120 degrees apart from each other. This one is also going to be nonpolar. Remember, we're skipping the hybridization for right now. We'll come back in a different video and talk specifically just about hybridization. But this is also going to be nonpolar. A couple different ways of visualizing this. The first is kind of more of a, you may have seen this in physics with vector additions. If you have vector additions, you would see that all the vectors would cancel out. Well, what does that mean? Well, that means that if we look at these diagonal things, remember we're looking at pulling out from that central atom. As we're pulling out, these diagonals could get broken down into a horizontal component and a vertical component. Well, this one on the right is as much to the right as this one is to the left. So the right-left direction would cancel out. But notice how they're both up from the central atom partially. Well, that would counteract this pull we're getting from the bottom atom. So these would all cancel out. This would be nonpolar. You can also think about this using our tug-of-war analogy again. If I had 3 equal strength teams that are all equally separated from each other, well, if they're equally separated from each other and they're pulling at equal strengths, no one would win this. So in this specific thing of BF3, this would be nonpolar. But now what I want you to do is imagine one of these outer atoms is different. Imagine this atom over here on the right was not a fluorine. Let's make it a chlorine or a bromine. That's going to have a different electronegativity than the other outer atoms. That would then make this molecule polar because there'd be a net pull. There wouldn't be a complete canceling out of everything. So for polar, nonpolar, you really have to look at what are the specific atoms you have. Here, they're all the same, so they're definitely going to cancel out because they're equal and opposite. But if one were different, well, if one were different, now I don't have equal strength poles, and that would have changed this to a polar molecule. So 3 electron groups are always going to be arranged in this trigonal planar fashion. We're going to get rid of these so we can build our next molecule. Our next molecule that we want to build is SO2. I'm going to build SO2 here. Swing this around so we can really kind of view what's happening with SO2. But SO2, remember, if you look at the Lewis structure, it has a lone pair on that central atom. Now, the number of electron groups, this has a little bit different counting than what you've seen before. If you have a double bond or a triple bond, that only counts as 1 electron group for this counting. We'll go back and talk about that a little bit more in a different video again, but double and triple bonds just count as a single electron group. So I have 1, 2, 3 electron groups. of those 3 electron groups, 2 of them are involved in bonds. I have those in there already. And 1 is a lone pair. So I need to get that lone pair in here. The lone pairs are kind of represented with a pair of dots. It's kind of where they would be situated in space. So if I'm kind of looking at this molecule, this is what this molecule looks like right now. So first thing we're going to do is we're going to look at the electron pair geometry. And the electron pair geometry, because I still have 3 electron groups, remember this double bond still counts as just a single electron group for this counting. I still have 3 electron groups. This lone pair counts as electron groups, 1, 2, 3. How are those electron groups arranged? Well, they're arranged the exact same way they were before in this trigonal planar fashion. Everything's arranged kind of 120 degrees apart for those different electron groups. So that stays the same. Anytime you have 3 electron groups, you're looking at a trigonal planar electron pair geometry. Now what changed in this, now that we started having our first example of a lone pair, is going to be the molecular geometry. Remember, the molecular geometry doesn't care what's going on with the lone pair. It's just interested in how are the atoms situated with respect to each other. So if you look at how the atoms are situated with respect to each other, well, it's not in a linear fashion. It's definitely not how I drew it on the flat 2-dimensional Lewis structure. These instead are not linear. If I go down and click the molecular geometry here, this is bent. It's not a linear orientation for that molecular geometry. Sometimes you still see it's not used as much anymore. Sometimes you still see the older terminology for this, which is, if I kind of move the molecule, kind of looks like a V. That's not used so much anymore. Usually it goes by bent now, but you still may see the older term of V shape for this. Now we can still look at the bond angle for this. Remember, bond angle is outer to central to outer, and the bond angle here is still 120 degrees. This is still a 120 degree angle here. Remember, we're skipping the hybridization for right now. So now if we go polar or non-polar, this molecule is definitely going to be polar. Even though these 2 outer atoms are identical to each other, they're both oxygens. We know they're identical because this molecule has resonance structures as well, where we could show this on the other one. So these oxygens are identical, but this is still polar because notice they're not situated equal and opposite from each other. They have equal strength poles, but they're not situated opposite each other. They're both below that central atom. So if they're both below and they start pulling, you're going to get a net pull directed down the way I have this shown right now. Another way of thinking about this is set up a game of tug of war. In the middle, instead of just a rope connecting everything, put a metallic ring. But now put the 2 groups playing tug of war, the 2 teams playing tug of war, not opposite each other. Put them 120 degrees apart and imagine them starting to pull. Well, if they start pulling and they're not equal and opposite, guess what's happening? Everybody's going to start moving down. There would be a net pull. This one is going to be polar. I'm going to kind of remove all of our things so we can build the next molecule. The next molecule we're looking to build is CF4. So I'm going to go ahead and build CF4, but when you're looking at the Lewis structure for CF4, look at that central atom. Count up those electron groups. You're going to see 4 electron groups on CF4. Of those 4 electron groups, all of them are involved in a bond, and there are no lone pairs. Let's go ahead and build this molecule. I need 4 things bonded. So this is what the molecule looks like in 3 dimensions. You can kind of rotate it around, looking at some of the different things here. But this is kind of a strange shape. This starts to become a shape we're not as familiar with anymore. So the name of this specific electron pair geometry is, if you were to draw faces on all of the different spots you draw faces on this, you would get a four-sided three-dimensional figure. A four-sided three-dimensional figure is a tetrahedron. So this is similar to a tetrahedron, so we call this tetrahedral, like a tetrahedron. That's how these electron groups, remember these are the sticks, are situated with respect to each other. So our electron pair geometry is tetrahedral. Our molecular geometry, here you have atoms at each of the electron groups here, no lone pairs. So your molecular geometry is also going to be the same as that electron pair geometry, also looking at tetrahedral. I already put up the angles here. They're 109.5 degrees. Well, we're not used to dealing with 109.5 degree angles as much, so this is definitely a molecule you want to spend some time thinking about interacting with, maybe using some modeling software or making your own model with just gumdrops and toothpicks to kind of get a visual of how this is going to look in 3 dimensions. Here, this one's, again, a little bit more difficult to see. This one's going to end up being non-polar if all of these outer atoms are the same. And there's a couple different ways to see that. First way is if I kind of orient the molecule like this. Kind of looks a little bit like a pyramid, maybe. You look at all 3 of these white atoms, they're all in the same plane. So if I move this around, you can see it. They're all in the same plane. So these 3 kind of on the bottom are all in the same plane, but they're all below the central atom, that purple atom. So being they're all below the central atom, these 3 are exerting a net pull downward. That's going to get canceled by the thing on the top, the atom on the top having that net pull upward. So this is going to be non-polar because these are all the same. They're all equally spaced apart from each other. Being they're all equally spaced apart from each other and they're all pulling the same strength, this would be non-polar. Now, if this one were different or any of these outer atoms were different, then it would change to polar. So if you had something like instead of CF4, maybe CF3Cl, replacing one of these outer atoms with a chlorine, now I have a different strength pole. Not everything would cancel out in this. And here is another good example of not getting trapped into looking at the molecule in your 2-dimensional Lewis structure. You have to go beyond that into these 3 dimensions. So if you can look back at the Lewis structure for that, the way I drew it, the bond angles kind of look like they should all be 90 and 180 degree bond angles in the 2-dimensional Lewis structure, but that's not the true bond angles in the molecule. The true bond angles in the molecule are 109.5 degrees apart from each other. Again, we'll go back and do hybridization in a different video. I'm going to take off this so we can build our next molecules. Now you're kind of on page 2 of this Vsepr table from the PowerPoint. And the next molecule we're looking at is NF3. So when you look at NF3, and again, we're looking at the central atom. And we're counting the electron groups on that central atom. When you look at the Lewis structure of NF3, you're going to see 4 electron groups on that central atom. Of those 4 electron groups, 3 of them are involved in bonds, and I have 1 lone pair. So I want to go ahead and build this molecule now. So we can kind of have a look at it. Now, the first thing we want to identify is how are the electrons situated with respect to each other? Well, the electrons are situated with respect to each other in terms of a tetrahedron or tetrahedral, just like we saw before. Remember, for the electron pair geometry, the lone pair counts. So I have 1, 2, 3, 4. They're all situated in a tetrahedral fashion. So I still have tetrahedral. Now the molecular geometry, though, when we're doing the molecular geometry, I'm just moving the molecule around. I encourage you to come on here and play with these molecules so you can kind of see how they're actually going how they're actually working, so you can kind of see these in 3 dimensions. The molecular geometry, we don't care about this lone pair. We're just looking at how are the atoms situated with respect to each other. And how the atoms are situated with respect to each other is kind of like a pyramid, where the central atom is kind of the peak of the pyramid, and the 3 outer atoms are the base of the pyramid. So the base of the pyramid is a triangle. It kind of looks like a pyramid. So it kind of looks like a pyramid. We would call it trigonal pyramidal for this. So looking at the bond angles again in this. The bond angles again in this are going to be 109.5 degrees. If I kind of move the molecule around so you can kind of look at these bond angles, you can see we're looking at 109.5 degrees going outer to central to outer for all of these bond angles that we have. Again, we're going to skip hybridization, but we do want to talk about the polarity. Now, all 3 of the outer atoms are on the same plane, and they're spaced equally apart, but they're all below that central atom. Being they're all below that central atom, you have no choice but to have a net pole going in some direction. So you're definitely going to have a pole going down in this. This is going to make this polar. A couple other things to mention again. The 3-dimensional structure does not look like how I drew it in the 2-dimensional Lewis structure. The angles in the 2-dimensional Lewis structure look like they should be 90 and 180. That's not what they are. You may even draw a Lewis structure kind of showing them equally spaced out, but in 2 dimensions, that looks like 120 degrees. Those aren't the angles. You have to take the information from the Lewis structure, and then using what we're dealing with here in these Vsepr tables in order to figure out how this actually looks in these 3 dimensions. I'm going to get rid of everything here so we can do our next molecule. Our next molecule is water. So I drew the Lewis structure for water really quickly. You count the number of electron groups in water. I'm looking at 4 electron groups. Of those 4 electron groups, 2 of them are involved in bonds, 2 of them are in lone pairs. So I'm going to go ahead and build this molecule, but right away, 4 electron groups is always going to match with a tetrahedral electron pair geometry. If I'm putting 4 electron groups, got 2 of them in from the bonds, now let me get the lone pairs in, you're always going to get this tetrahedral electron pair geometry. 4 electron groups always matches with tetrahedral electron pair geometry, just like 2 always matches with linear. 3 always matches with trigonal planar. 4 total electron groups will always match onto a tetrahedral electron pair geometry. So our electron pair geometry is still going to be tetrahedral. Go ahead and put that up on the screen. Now the molecular geometry, remember the molecular geometry, we don't care about the lone pairs. Lone pairs are occupying positions, but we're just trying to describe how are the atoms situated with respect to each other. And we mentioned this previously in the Lewis structure video, but water is not linear. Water is bent. So we're going to see a bent shape again. You could also call this V-shaped again. But this is very, very important. This is a different bent than we've seen. If you go back and look at SO2, we also described SO2 as bent. But that bent had 120 degree bond angles, where this one has 109.5 degree bond angles. Why the difference? The difference is because even though these have the same molecular geometry bent, they come from a different electron pair geometry. Remember, the electron pair geometry for SO2 is trigonal planar. That's what gave us those 120 degree angles to begin with. Meanwhile, this bent comes from a tetrahedral electron pair geometry. So this bent is going to have bond angles of 109.5 degrees for this one. In actuality, in water, you're going to see that the bond angle here is actually less than 109.5. It's about 104.5 degrees. And the reason being is the molecule actually scrunches down a little bit more, trying to get, for these outer atoms, trying to get away from the lone pairs. Things kind of really try to get away from the lone pairs. That's going to reduce this angle somewhat. You don't need to necessarily worry about that. You can write down and view it as 109.5, but just as you're looking and talking about other things that involve water, you're going to see that's not quite 109.5. It's actually less. That's due to that scrunching down of the molecule. We want to decide, is this polar or non-polar? So again, we're looking at the poles. Which things are actually going to pull? We're looking at the pull of the outer atoms on that central atom. Well, here, my outer atoms are the same, but they're not spaced equally apart. It's not 180 degrees apart. It's 109.5 degrees apart. So as a result, there will be a net pull. Again, if you tried to play this as tug of war and you had two equal strength teams, but they weren't completely opposite of each other, everyone would be moving a direction. In this case, if both teams started to pull, everyone would be moving down in this. So this one is definitely polar. I'll go ahead and clear off everything for water. And we're going to do our last specific molecule for this video. There's going to be a second video on this, but I kind of want to start with the very beginnings of this. The last one for this video is going to be HF. And I drew the Lewis structure out for you. Normally, when you only have two atoms, you kind of have to decide, okay, which one's the central atom, which one's the outer atom? Well, we know hydrogen can't really serve as a central atom. So for this, we want to view fluorine as that outer atom. And if you're looking at Lewis structure on fluorine, you're counting the electron groups. On fluorine, you're going to see 4 total electron groups. Of those 4 electron groups, I only have 1 bond, but 3 lone pairs. So let's go ahead and build this molecule. 1 bond, 3 lone pairs. So I'm going to kind of situate this the same way that I drew the Lewis structure of this. And again, first thing I'm going to look at is the electron pair geometry. How are all the electrons situated with respect to each other? Remember, for the electron pair geometry, the lone pairs count. So anytime you have 4 electron groups, for electron pair geometry must be tetrahedral. So here I have a tetrahedral electron pair geometry, as we saw before. 4 electron groups always matches onto tetrahedral. Now when I'm looking for the molecular geometry, how are just the atoms situated with respect to each other? So the central atom and the outer atom, well, anytime you only have 2 things, you kind of have to call that linear. And can't really show the bond angles, not going to list it because it's not outer, central, outer, because I only have 2. But you kind of look at this and you say, well, if I'm using linear as a molecular geometry, I have to call the bond angle 180 degrees. You don't really have a choice but to do that. Hybridization, again, we're going to come back to in a different video. And we're asking, is this polar or non-polar? Here, when you only have 2 things, you're not using the central atom as kind of that ring or that pull from where everybody else is pulling. But here, the central point's kind of right between these 2 atoms. And here you just have to ask, who's more electronegative, fluorine or hydrogen? Well, fluorine is more electronegative than the hydrogen is, so I'm going to get a net pull directed at fluorine. So this one is definitely going to be polar. So that's going to conclude this first Vsepr video that kind of shows the basics. But right away, a couple key take-home things you want to grab just from this first one. The first thing is that on your Vsepr tables, these things you should be holding in your hand right now, these tables that you printed out from the PowerPoint, first thing you want to kind of look at is there's some correspondence between a couple of the columns. And it's the first column, the number of the electron groups, and the electron pair geometry. Go ahead and go back and look at this. If your number of electron groups is 2, your electron pair geometry will be linear. If your number of electron groups is 3, your electron pair geometry will be trigonoplanar. 2 always matches with linear. 3 electron groups always match with trigonoplanar for that electron pair geometry. 4 electron groups will always match to a tetrahedral electron pair geometry. You will always see those matchings. That's the very first thing you really want to look at when you're doing these. Is first, number of electron groups match onto the electron pair geometry. 2, linear. 3, trigonoplanar. 4, tetrahedral. The second thing that you want to already be starting to grasp from this is that whenever there are no lone pairs, we did 3 examples with no lone pairs, okay? The BeH2, the BF3, and the CF4. All those had no lone pairs on the central atom. And what you'll notice is whenever you have no lone pairs on the central atom, your electron pair geometry is always going to match your molecular geometry. That's because with no lone pairs, every electron group is going to be involved in a bond. So that means you're going to have matching between those if you don't have any lone pairs. So this is our first video where we went through 2 electron groups, 3 electron groups, and 4 electron groups. We're going to have a second video where we deal with 5 electron groups and 6 electron groups. So be on the lookout for that kind of coming up really, really soon.